We can get to the main event tonight, which is Dr. Doug Clowe from Physics and Astronomy, A Dark and Lonely Place, Dark Energy and the Future of the Universe. It's all yours, Doug.
So the past couple times I've done these science cafes, I've talked about what we call the dark sector. And the dark sector is the portion of the universe that we're pretty sure is there, but we can't see. All right? So I'm going to skip over sort of my standard introduction, and because we have a lot to go over in terms of what this stuff does. But here's our viewpoint of what makes up the universe right now. So it's sort of pie chart technology. These things that aren't blue, that's the stuff that we actually know about. And just to give you an example here, here's our content of all the stars in the universe. So the sun, everything that we see up in the night sky, all the other galaxies that we can see when we point very big telescopes at them, they make up less than 0.5% of what we think is present. Right? Most of the stuff that we know about is actually in the form of hydrogen and helium that's never been dense enough to collapse under its own gravity and form a star. So these are just sort of giant gas clouds drifting between space. We can take a census of them. Sometimes they get near enough that they become heated up by starlight and we can see them glowing. Other times they will absorb light that's passing through it and we'll see missing light from where it should be. And so we can get a census that way. But both the stars and the hydrogen and helium clouds are basically hydrogen and helium. It's 25% helium, 75% hydrogen, pretty much. The stuff that we're mostly made of, the carbon, the oxygen, the nitrogen, all that sort of stuff, all that has been produced inside of stars since the universe began. It's been pushed back out by supernova and planetary nebula and dying stars and that sort of stuff. And stars don't produce a lot of it, because you can only have nuclear fusion occurring at the very center of the star. So as a result, everything that's not hydrogen and helium that's made up of protons and neutrons is only about 0.03% of the mass of the universe. And then there's these funny particles called neutrinos that you can come and ask my nuclear physicist colleagues about. They'll be happy to talk about them. They make up something like 0.3% with an error budget of roughly 100% because we don't know what their mass actually is. Right? But it's going to be small. All right. You add up all of these, you come up with a number that's less than 5%. The other 95% is stuff that we can't see. But we know it's there because of its influence on the stuff that we can see. And normally, most of my research is talking about dark matter, and that we see from its gravitational influence. It's what holds galaxies together. It's what holds clusters of galaxies flying apart. Around, and so we know it's there. I'm not going to talk about that this time, but we know that makes up about 25% of the mass of the universe, so it's 5 times more common than protons and neutrons in terms of mass. I'm just mentioning it right now because I'm going to come back to it at the very end, because it matters as to what dark matter is in terms of what happens to the universe a little bit. But even dark matter is a small constituent. The vast majority of the universe, 70%, is what we call dark energy. And to try to understand what dark energy is, we really have to go back to the very beginnings of sort of modern astronomy and go through a little bit of the discovery process to understand, because in the end, what I'm going to tell you is that dark energy right now is a mathematical term in an equation, and we're struggling to figure out what it could be. Right? So how did we come to this? How did we come to a universe in which this stuff might actually be the dominant force? All right. As far as we know, you can't actually use dark energy for anything, so that's probably not the solution. Okay, so let's go back about 105 years. So if I were giving this talk in 1913, here's what you would have learned. You would have learned that there are a lot of stars that we can see in the sky, many more than we can see with our eyes. Telescopes, you keep seeing fainter and fainter stars. These stars seem to be arranged in a consistent structure that's gravitationally bound that we call a galaxy. The name of our galaxy is the Milky Way due to its appearance in the sky. In addition to stars, we also know there are gas clouds around, which we call nebula. There are different types of nebula. Some of them have these weird spiral structures in them. Some of them look like they're just fuzzy gas clouds. There was a raging debate at this time as to whether any of these nebula are in fact galaxies outside of our own, or if all of them are just gas clouds, right? There was sort of, the astronomy community was split evenly. No one had any conclusive evidence either way. And so we didn't have anything firm that was known to be outside of our own galaxy. So we lived in what we called the island universe, where you have a single galaxy, and outside of it was just empty space, right? Because of that, we also thought that this universe was static. We didn't know how long stars lived, but we figured that there was enough gas around, you would just keep making stars, and therefore the universe could have been infinitely old. We didn't know. It could also been formed at any given point. Right? Into this picture came Einstein. And Einstein, in 1915, developed his theory of general relativity. And the main reason why he did so was because the planet Mercury was not obeying Newton's laws, and its orbit wasn't correct. And so there was a need to figure out why the orbit of Mercury is different from all the other orbits, and the answer is because as you increase gravity in general relativity, you break away from the Newtonian gravitational force law, right? So he had to come up with this whole theory to show that, and then he and colleagues started experimenting with this theory and saying, okay, well, if this is true, what does it tell us about other stuff? And much to his shock, was he found that when you use general relativity, space is not static. Space is either getting bigger or it's getting smaller, depending on the universe that you live in. But it can't remain stationary with what he derived, and that's because gravity is actually basically curvature of space, and it's pulling on space itself. And so if you have anything in your universe, gravity is going to cause the universe to start collapsing in on itself. And he didn't want that to happen because, again, the scientific consensus was space was static. We lived in a static place. And so he went back over all of his terms, and he went through all of his math, and he found that there was one place where he could insert a number. And that number would not affect anything except the rate at which space expands and contracts. And so if he inserted a number and made it one specific value, he could counter it, and he could stop the universe from expanding. And so he gave this the Greek letter capital lambda, and he had a static universe. Well, shortly after that, we made a couple discoveries. The first one occurred in the late 1910s, and that was the fact that when they looked at these funny nebula that have the spiral structures, and they went and they took a spectra where they break up the light as a function of a wavelength, so that you can now start seeing lines here, which are caused by atoms with the electrons moving around. You can do this in a chemistry lab here on Earth. You can measure the wavelengths that they're supposed to be. And they looked at these wavelengths as they were coming out of these nebula, and they found they were all too long. All of them have been shifted. And they've all been shifted consistent with what we call a Doppler shift. Right? Doppler shift is something is moving away from you. All the light that it emits gets redder, gets to longer wavelength. Right? It's the same principle that we use to catch you speeding on the freeway, or cops use. Doppler weather radar, same idea. But when they looked at these nebula, they could tell that not only were they all moving, for some reason, all the ones that had the spiral structures in them, they were all moving away from us. That was a bit odd, right? But still nothing too concerning. You go forward another 10 years, and then we had a new astronomer, Edwin Hubble, who had a new telescope in which he was now able to look at these spiral structures, and he could resolve individual stars in them. And he found that some of those stars were ones that should have a certain brightness. And so he could measure how bright he saw them, and he knew how much or how much light they should be emitting, and so he could measure how far away they were. And the answer was they were way outside of our own galaxy. They were much further away than any star in our own galaxy is, which meant these spiral structures were actually other galaxies. And then he started plotting the distance that he measured these galaxies from, which is this axis, versus the speed at which they appeared to be moving away. And he found a nice relation. The further away something is, the faster it appears to be moving away. Right? So this is known as Hubble's law. This is what he actually published. If we take a modern version, which has a bunch of things corrected, what you get is something more like this. So each of the little black points here is a galaxy that's nearby us. Here's the distance, here's how fast it appears to be moving away. And basically this red line that goes between the two, that is something that says that the velocity that it's moving away is a constant number times the distance that it is from us. And so this constant has become known as Hubble's constant, and it's telling us the rate at which things appear to be moving. Okay? When you go and you ask, okay, well, what does this mean to the universe? And when this was first discovered, everyone assumed this meant that the galaxies were actually physically flying away from us. So we'll go with that interpretation for a little bit. Here I just have a cartoon diagram, I'll get out of the way, in which we start with galaxies. So we had one that was 1 light year and one that was 2 light years away, or a million light years. And we allow them to expand. This one's twice as far away, so it's moving twice as fast. So after you let it expand for a little bit, it was a 2-to-1 ratio, now it's a 4-to-2 ratio, which means the ratio has stayed the same. Okay, so that's what Hubble's law means. So if instead of this random picture, I instead give us a grid, and I put us in the center of the grid, and I allow the grid to obey Hubble's law, this is what you see. Right? The points that are further away are moving away faster, so they stay in this grid formation. As they expand, it's just the grid overall gets bigger. Right? So now I'm going to put some blue dots where they originally started, right? And we'll have the red dots expand over a small amount of time. And so here we are apparently not moving from our own point of view. If we go in any direction, you'll see that as we go from starting positions, right, they start moving further and further away in this constant amount of time. So now mentally invert that. What happens as we move backwards in time? All of those points will wind up back on us at the same moment in time. And that was our first realization that the universe is not infinitely old. It appears that everything is collapsing back on us, backwards in time, and so we can calculate how fast things are moving versus how far away they are right now, and you get an estimate of how long would that take, right? And that gave us an estimate that was about 13 billion years. Right? Now, this is unusual. In astronomy, we obey a law that says we are not in a special place. Everything that we see, everyone else should be able to see. And a special place is at the exact center of something. Right? And so this would seem to violate astronomy until we started looking around saying, okay, well, what would a person over here in this galaxy see? So this is just everything moving. And so we can take this person's velocity and subtract it off of all these other points so that we get the point of view of what does this galaxy see. So if we do that, right, we have this galaxy staying stationary, and what we have is the exact same pattern. Every galaxy surrounding that galaxy appears to be moving directly away from it, and the further that you get from the galaxy, the faster you appear to be moving, which means Hubble's law works everywhere. Every place sees itself as the center of the universe, and everything expanding back, and every place sees all the other galaxies collapsing back on itself. Right? So, what does this mean for where is the center of the universe? Well, the answer is we don't know. Right? If we had something like this occurring here on Earth, an explosion does this. You have everything in one place. That was not planned. Right? And things that pick up a little bit extra velocity during the explosion will wind up further away. But you always see an edge to the debris, and so you can draw circles and figure out where did it start from. When we look at the universe, we got bigger and better telescopes, and we start looking at fainter and fainter stuff, which winds up being further and further away. And so the first thing astronomers were looking for is, when do we run out of universe? And the answer was we don't. We can keep getting better and better telescopes, and we keep seeing further and further away until we actually run out of time. And that's because as the light travels to us, it can only move at the speed of light. And so as we are looking further and further away, we're actually looking into the past. And we're looking further and further into the past. And eventually, we reach the point where everything was collapsed down at this single point, and we run out of universe. We can't quite see all the way back to that point, but we can get pretty close. Right? So we don't have an edge, at least within what we can see. We can only see galaxies which light can travel to us within the age of the universe. And so we know that the universe is at least this big. We don't know how big it actually is. It might be infinite in size for all we know. We just know a minimum size. Right? But as we keep looking further and further away, we have Hubble's law that says the velocity keeps expanding. And eventually, by the 1940s, we got telescopes that were good enough that told us that we have galaxies that are now moving away from us faster than the speed of light. And that's a problem, because general relativity, which had been shown to be correct by then, says nothing can move faster than the speed of light. So what's going on? Well, the solution goes back to what Einstein had discovered in 1915 when he looked at what general relativity was predicting. It's not that these galaxies are moving further away, it's that space is getting bigger. All right, so what does that mean? Right? So to try to give you an idea of a way to think of this, imagine that you're an ant and you're living on the surface of a balloon. You have no perception of up and down. You only know this two-dimensional structure that you appear to be living on. You don't even know that this balloon is curved because it's much bigger than you are. Right? Now, we'll tape a couple different positions on it and allow that balloon to blow up. Right? So the balloon is moving out radially in all directions. You're an ant. You don't know about up and down. So from your point of view, none of these objects are actually moving. Right? Because they're only moving perpendicular to the surface which you're standing on. But you can measure the distance because you can walk between them. And what you're discovering is that the distance between them is increasing over time, even though the objects are not physically moving with respect to their surroundings. Right? So this is an example of an increasing space. Right? It's not a perfect example, because in this example, we're expanding something out into an extra dimension. And as far as we know, there are no extra dimensions that we're expanding our three-dimensional space out into. Right? It's just that we're creating more space as we go. And as you have space, it just increases. So the galaxies are not moving with respect to their local surroundings, unless there's another galaxy with gravity sort of tugging on it. But the Hubble law that we see is not velocity, it's space getting bigger. Right? So what does this mean for redshift? If the galaxies are not moving, why do we see these apparent Doppler shift? It's because if you have your space getting bigger, you can think of the photon having a wavelength that occupies a certain amount of space, and as it travels and the wavelength and the space stretches, the wavelength of that photon will stretch right along with it. So what we're really measuring when we measure the redshift is not a velocity. We're measuring by how much has space stretched since the light was emitted. And so what I can tell is that if you are looking at something that has a redshift of 0.1, that means that the wavelength is 10% longer than it was when it was emitted. That means the universe has expanded in size by 10% since then. If it's a redshift of 1, the universe has doubled in size. Right? So 1 plus redshift is basically the factor that has expanded by. All right. And so you take this, and you now go back to Hubble's law, and we can now see that what we can measure easily from our data is we can measure by how much has the universe expanded since this photon was emitted. And then if we know how far away something was, that gives us the rate that the universe has been expanding over time. Okay. All right, so where do we go from this? Well, this is a graph that basically shows the rate at which the universe is accelerating. So on this axis we have time, and we're sitting here where we set t equals 0 is now. So this is us. And regardless of what sort of universe we're sitting in, what we do know is the redshifts of all these galaxies whose light is coming from us. And we know the rate at which we see the universe expanding right now because of Hubble's law. So the rate at which we see the universe expanding is basically the slope of this line. And so we know that all universes that are valid must have the same slope where we are, because we can observe Hubble's law. And we know that the galaxies are a certain distance away currently, and therefore you see everything here winds up on the same point. The vertical axis is sort of some measure of how fast the universe is expanding, And in this case, we're plotting it as sort of the average distance between galaxies. So as the universe is smaller in the past, the average distance between galaxies decreases. If the universe gets bigger in the future, this average distance will increase. All right, so if we look backwards in time, which is this half, we can ask, okay, what's going to happen? And if the universe is empty, if there's no matter anywhere, then it's expanding at a certain rate. It'll just keep expanding at that same rate forever. And that's this blue line that we call a coasting universe, just a constant slope. If there's matter, then matter exerts gravity, and you have to overcome that gravity to expand the universe, the same as if you throw a ball up in the air, right? Gravity slows the ball down, eventually stops it, and returns it to Earth unless you throw it really fast. Still slows it down, though. So if we have matter, and therefore gravity, what we expect is the expansion rate of the universe should be decreasing over time, right? And that's what we show here, where these slopes become steeper and steeper and steeper. So this is a universe which is decelerating, as is this green universe, and the differences between them is how much matter and therefore how much gravity. The more matter you have, the faster you are decelerating, and therefore the faster you had to been expanding in the past. Right? And this point where it reaches the horizontal axis, this is the point where all the mass is back on the same point. And so this is the point where we think that we have a beginning of the universe. Right? So at the current rate that it's expanding, if it stays constant, the universe would last about 13 billion years before we reach that point. As you add mass to the universe becomes younger and younger because you were expanding faster and faster back in the past. Right? If for some reason you can have a universe which is accelerating its expansion rate, you do the opposite. It was expanding slower in the past, and therefore it took longer to get to our point. All right, how can we tell the difference between these? Well, remember that what we can measure is we can measure the redshift of the light. We can measure how much longer it is. And if we know how bright an object intrinsically is, we can measure how bright we see it as, and that lets us get a distance measurement to it. Okay, so if we can find things that we call standard candles, objects that we know are in different galaxies that should all be the same intrinsic brightness, we can measure their relative brightness and determine what is the distance to these galaxies relative to each other. All right, so how does that help us? Well, if we consider two universes, we have our universe where we're expanding at a certain rate, and we have another universe which is expanding faster. Right? We know that these two galaxies in these two universes are emitting light, and that light is traveling the same distance to reach us. So over that distance, the universe in our universe would have expanded so much, and you'll get a certain redshift. In the second universe, which is expanding faster, you're moving the same distance. You're getting more expansion per distance, which is what Hubble's law is giving us. That means you wind up with a higher redshift. Or if we invert that, if what we measure is a single redshift, what we see is the galaxies in the faster expanding universe must be closer to us because they will have picked up that redshift in less distance traveled. Which means that if we go to what we would see in terms of the objects, right? An object, as it gets further away from you, it gets dimmer because the light is getting spread out over a larger area. That works in our expanding universe model too. And so we can measure how bright something is in different galaxies that we think are of similar brightness. And if the object is brighter than we expect, that means it's nearer than we expect, which means the universe has been expanding faster. And if it's dimmer than we expect, it means it's further than we expect, which means the universe has been expanding slower, because what's constant is how much has it expanded since that light was emitted. All right. I'm hoping I didn't just lose everybody. Okay. The reason why I have to do this is our picture of the universe changed 20 years ago. Is prior to 20 years ago, so if you go back and you find an old copy of Stephen Hawking's a brief, whatever it's called, you find one published before the late 90s. What he would have talked about is these three universes, right? So if we look into the future, the difference between these three universes is this is the coasting one, where you're always expanding at the same speed. This is known as a critical universe, where you are slowly slowing down, and as time goes to infinity, you approach zero expansion velocity. And then if you have more mass, you have enough gravity that you can actually stop the expansion and start the universe collapsing again. And this all has to do with how much mass is present, right? No one expected the universe to be accelerating. Because to get the universe accelerating, you have to have something pushing on it. And the only thing was this funny mathematical term that Einstein had, and everyone agreed that once that term wasn't needed to keep the universe static, it's probably just zero. So you should probably just ignore it, right? Well, so people went out and found one of these standard candles. It's called a type 1a supernova. What it is a white dwarf, which is an old dead star of about the sun's mass, or maybe twice as much, made up entirely of carbon and oxygen. If it can gain a little bit of additional mass by basically adding stuff onto it, it will eventually explode in a supernova. And because these are all basically the same mass when they explode, they're all about the same brightness. And so this is our standard candle. If we can find these type 1a supernovas, we know that they're all about the same brightness, and therefore we can measure the relative brightness between different galaxies and get the relative distance between these galaxies. And by the late 90s, we had enough surveys covering enough areas that we could find these things. The rate at which they occur is you get about one of these per century per galaxy. So you really have to cover millions of galaxies for a couple of years before you have enough to build up statistics. And this is what they actually saw. Yeah.
I got a question.
Oh, yeah, question.
You mentioned we know these are the same brightness.
Yeah.
How do we know? Because the physics far away might be different than the physics here.
Right. So how do we know?
Some assumptions
So
built into that.
it is in that we are assuming that basically nuclear fusion works the same way. I would have to go into a long description of fundamental constants of nature and that sort of stuff, right? So I can talk to you afterwards, but yeah, basically people have done various tests and they don't see any difference between these constants whenever we're able to measure them. Okay, but all right, so we have these supernova, and basically what I have a graph here is the brightness that we see them at versus the redshift that we measure them at. And the important thing is the red line is an accelerating universe where the Hubble constant was smaller in the past. The blue line is a decelerating universe, which was what we would normally expect. And you see the red line goes through the data points much better. This was 20 years ago. This is the observation that basically won the Nobel Prize a while ago. It tells us that the universe has been accelerating. All right. All right. So. And I should say that over the past 20 years, we've come up with other ways of measuring this that don't involve exploding stars. And they all basically agree with the same picture. Okay, so we now have multiple pieces of evidence that all say the universe has in fact been accelerating. Right? If I go back to my old graph and I put those data points onto this graph, it looks like that. Right? So they're falling on the yellow curve. That tells us that it's expanding. All right, so I have an accelerating universe. I need something that causes that acceleration. I go back to Einstein. I say, okay, well, I take this lambda term, which was just a number he threw into an equation. I can fit that equation to my data. I can come up with a number for a value that it is. And that's where we get that lambda winds up being 70% of the mass of the universe. All right, I have a term in an equation. What is it? We don't know. That's the short answer. Right? The simplest explanation for it is that it's an energy field. Right? What is an energy field? Well, energy fields kind of permeate everything. They're of constant density everywhere. They don't react to gravity, and things move through them. So we have an electromagnetic field that photons move through. You might have heard about the Higgs field that was shown to exist by the Large Hadron Collider. That's a field that particles move through and they gain mass by moving through. This would just be another one of these energy fields that we use in physics. It would basically be an energy field. It needs to have a negative pressure, and by having a negative pressure, that allows it to push against the rest of the universe and cause the acceleration. Does it have to be that? No. There are many other things that it could be. One option is gravity gets much weaker with distance than we think. That would appear that what we're seeing is not an acceleration, we're seeing a lack of a deceleration. We have other ideas out there. My favorite one to explain of how crazy they can become is in order to understand all the particles that we know about, particle physics wants 5 dimensions. It has 3 spatial dimensions, it has time as a dimension, and then it needs this 5th dimension that's sort of rolled up on itself in order to get the forces that hold nuclei and protons together. That's 5. String theory, if you've heard about that, which is this idea that everything is just oscillating strings somehow interacting, it needs 11 dimensions to work correctly. So we need 5 dimensions for what we observe in particles. String theory wants 11. So what we can do is we can take this 5-dimensional universe that we're sitting in. We can take this other 5-dimensional universe that's set off from ours. We have 1 dimension left, which is a string dimension that connects every point in our universe to every point in this other universe. You don't allow light to go across the string, but you can allow gravity to go across the string. And then the strings can sit there and oscillate, and dark matter becomes the mass in the other set of dimensions. And dark energy becomes, as these two things oscillate along the string, it's basically a tension, equivalent to a spring kind of operating. Bizarre, untestable, but allowed. All right? So that's sort of the first takeaway, is dark energy, we're not entirely sure what it is. We've been going through and testing it as best as we can, and it seems to be constant. We know from the equations it comes from, it has to be constant in space. It doesn't have to be constant in time, but our best measurements right now says it is, which gets rid of some of these weird ideas. But if it is what we think it is, and it is just this energy field that has a negative pressure and is pushing against itself, it leads to some very interesting consequences for the future. Right? So I promised in the advertisement that I was going to do a quick history of the future of the universe, or a quick future. Okay, so I'm going to violate one of the rules of Science Cafe and start putting up bullet points, just to remind myself not to skip anything. Okay, so let's talk about the near-term future. What's going to happen over the next 5 billion years? From cosmology, not a whole lot. From the Milky Way's point of view, it's going to be pretty dramatic. From our point of view, it's going to be pretty bad. All right, so the sun's slowly getting brighter. Why is the sun getting brighter? It's because we're starting to run out of hydrogen. We've used about half the hydrogen in the core. The core has to contract to keep the fusion rate and the pressure up. It actually overfuses when it does that. We start producing a little bit extra energy. It's not a fast rate. It's definitely not responsible to the global warming that we've been seeing over the past couple decades. But over the course of 100 million years, it's going to increase the luminosity of the sun by about 10%, which is bad, because as we increase the luminosity of the sun, we're going to get more heat on the Earth. We're going to start evaporating the oceans. That's going to get us a runaway greenhouse effect. That's going to increase the temperature even more. That's going to evaporate the oceans even more. And within somewhere between 300 million to 1 billion years, we're basically going to lose all water on the Earth. It's all going to be steam in our atmosphere. Given that we rely on liquid water for life, that's pretty much the end of life on Earth as we know it. The ratio, why is it a few 100 million to 1 billion years? It's uncertainties not in the rate at which the sun is going to increase its luminosity. It's the uncertainties in that runaway greenhouse effect. Most measurements I've seen are currently now, the models are predicting more about 300 million years. All right, so yeah, not in our lifetimes, but we do have a clock is ticking for life here on Earth. In about another 5 billion years, it won't matter anyway, because the sun's going to die. Basically, it'll run out of hydrogen entirely in its core. It'll collapse down. It'll become a red giant. And then eventually it will turn into a white dwarf. Right? At that time, the red giant, it will engulf Mercury and Venus. It may or may not engulf the Earth. Different models predict different things. So the Earth might survive, but it won't be habitable anymore. All right, at about the same time, the Milky Way is going to get destroyed. And that's because there's another giant galaxy that we're in orbit with. And we're basically heading right towards each other. There's still the possibility, we haven't measured how much it's moving sideways yet. So there's the possibility that instead of going straight on, we might just do a near miss. But even a near miss gets you a gravitational force that's going to fling the disk of the Milky Way apart. In the end, over the course of another 5 billion years or so, all those stars are going to reassemble. We're going to have a super galaxy. made up of both of our galaxies. That will start pulling in all the other galaxies surrounding it and ripping them apart. And so what we call the current local group, in about 10 to 15 billion years, will just be a single giant galaxy. Right? When this occurs, stars that are there will probably survive. It's very rare to have stars hit each other, even in these sorts of collisions. The nearby planets, which are the ones that are usually in the zone where we can have liquid water, will probably survive. Some of the further away planets might occasionally get ripped away. But you will survive. So life will survive that, maybe not on every planet, but definitely on most of them. Okay, so assuming that we've expanded out by now and have colonized the galaxy, it'll be an eventful time, but you'll survive that. All right, so that's the near-term future. Let's go a little bit further away. 100 billion years. I should say that between 5 billion years and 100 billion years, not much else is going to happen. Stars are going to get born, they're going to die. We're going to have fewer and fewer stars active because we're going to start running out of gas. But if you have an interstellar civilization that can move between stars on timescales of 1 million years, you have no problem. You can move around. All right. However, interesting things start happening to our universe, right? So remember, we said that redshift is the expansion rate of the universe as you are moving the light from a galaxy to us. So if we consider an expanding universe, which is accelerating, we have a galaxy that has a certain distance when a photon is emitted. It travels to us. Over that time, the universe has expanded by so much. So which means that when we detect that photon, if we then look at a photon that is now being emitted again by that galaxy, the galaxy is now further away, so it has to cover a greater distance to reach us. And if the universe expansion rate has been accelerating, that means that the expansion rate is also accelerating along with the distance, and the two effects feed against each other. And these galaxies start becoming further and further away very quickly, which means eventually these photons stop arriving, because the distance between us and that galaxy starts getting larger than the speed of light, right? And so galaxies over time in this accelerating universe, the redshifts become larger and larger, which means it gets harder and harder to see them. The distance increases, so they get fainter and fainter, and we can no longer detect them, right? How fast does this occur? Well, every object that we currently see at z greater than 2, so redshift greater than 2, the light that is currently being emitted by that object will never reach us. So we can still see those objects because they were much closer when the light that we're currently seeing was emitted, but they're eventually going to disappear. And as the universe keeps accelerating faster and faster because of dark energy, they're going to disappear more and more, and our observable bubble is going to shrink down. By about 90 to 100 billion years, that observable bubble will shrink down to exclude every galaxy that is outside of our own. So civilizations 100 billion years from now, their picture of the universe is going to be exactly what we saw back in 1913 when we didn't have very good telescopes. They're going to see that they're in an island universe and there's nothing outside of them, which means they won't know anything about cosmology or being in an expanding universe. What they will know, however, is they're running out of gas. All right? In 10 to the 14 years, our current process of powering the universe runs out. Right now, we take gas clouds, we collapse them down into stars, we have fusion produce power, and that emits light and heat back out into the universe. Every generation of stars, we lose gas. We lose protons and neutrons because we lock them up in structures that can no longer produce energy. So some of them are locked up in planets. The planets have no way of producing energy, so they just get colder and colder after their stars die. Brown dwarfs are objects that are too small to start nuclear fusion. So it winds up being about 8% of the sun's mass and below. They can't do nuclear fusion. So they just collapse down into an object and then just get colder and colder, same as planets. White dwarfs, neutron stars, and black holes are all remnants of stars when they die. When they die, some portion of their mass gets pushed back out into interstellar space, some portion gets trapped in these remnants. And the portion that's trapped in the remnants usually stays there. So in 10 to the 14 years, we will have run out. The cycle will have used up all of the available gas, and there's no more stars to create. It's also about the lifetime of the oldest of the lowest mass stars. And so those will turn off. We're out of stars. We're out of ways of producing light. Everything gets very dark. Occasionally you'll get flashes because we still have these white dwarfs and neutron stars, and they will occasionally hit each other. And when they hit each other, they will explode. But it's just the occasional flashes of light. Otherwise, the universe becomes very dark. All right. Step forward another factor of 10 to the 6. We're up to 10 to the 20 years. We have, after 10 to the 14 years, we basically have a galaxy, which is a whole bunch of individual objects that are pretty small compared to the distances between them, but they're still orbiting around, and they will get flung around by gravity. Every once in a while, they'll hit something. It's a very rare event, but it will eventually happen. And if you give yourself 10 to the 20 years, what you get is every object in the galaxy will, on average, have hit something. And that usually means they will start getting sucked into black holes because they will have hit a black hole at some point. And so you will sometimes have interactions where one of the objects picks up enough velocity it can get tossed out of the galaxy. So those objects will survive. They will just be out in intergalactic space. Everything else winds up in a black hole. And in fact, because of the way it works, most everything else winds up in the central black hole. So our galaxy becomes a giant black hole at the center with some smaller black holes orbiting around it that slowly get absorbed as they get flung around. Okay. All right. The very distant future. So we're past 10 to the 20 years. Next one is a bit speculative because we don't know this is actually going to happen, but we have reasons to think protons are probably not stable. We think protons are probably going to decay back into quarks. So 3 quarks make up a proton. Our current lower limit for this from experimental evidence is something like 10 to the 34 years. The current upper limit from theory is about 10 to the 40 years. So this is one that we're not entirely sure this is going to happen, but unless there's some fundamental physics that we're missing, it should. Which means all the protons are gone. So no more atoms. So what's going to happen, and also when you do this, if you take a proton and you look at the mass of the quarks that make it up, those quarks make up only about 1% of the mass of the proton. The other 99% is binding energy holding the quarks together, which means that when you disassociate the protons, you're also disassociating 99% of the mass. You're emitting it as light, which means these small objects that were being held together by gravity, they now only weigh 1% as much. They have some energy from disassociation. They're going to fly apart. So you're basically going to have just black holes at this point and then isolated quarks floating around. Even the black holes, so objects not in black holes are going to decay and fly apart. Even the black holes at some point are going to evaporate. This is called Hawking radiation. It comes from something called pair production, where you create a particle and an antiparticle. You suck one of them into a black hole. You leave the other one out. That mass has to come from somewhere. Only place it can come from is the black hole. And therefore, you slowly evaporate the mass of a black hole. It takes a long time. You're up to about 10 to the 100 years. But once you've done that, you're now sitting in a galaxy, which is just quarks and dark matter, assuming dark matter is stable. We don't know what it is. It might not be stable. It might decay like protons do, in which case the galaxies themselves will fly apart because they're losing mass too. And so we either have isolated galaxies of quarks and dark matter, or we just have isolated quarks and whatever dark matter decays into flying in interstellar space in this increasingly accelerating expansion universe that eventually gets to this basically exponential growth phase. Everything basically becomes pure dark energy. That's the end of the universe as we know it. That's why I called this a dark and lonely place. Right? However, there is possible hope. And possible hope comes from hand-waving about quantum mechanics. Last slide, I promise. Okay. What is the possible hope? Well, the universe is this pure dark energy almost, because we keep creating dark energy as we expand. This dark energy field is pushing the universe apart because of its density. So if you can get a portion of this dark energy field to suddenly have increased density, it will push that portion apart even faster. How do you do this? Well, it comes from the portion of physics called quantum mechanics, where the idea is you just have random stuff happening. And you can borrow energy against itself and suddenly create energy someplace. It just has to go away eventually. All right. We know this happens. You can go, we have a particle cloud machine over in Edwards sometimes set up, particularly at the Physics Open House. And what you will see is periodically particle and antiparticle just appear, they move around for a while, they come back and they collide and they disappear. This isn't the energy turning into a particle, this is the particles just appearing and then disappearing and that energy disappearing. We know this happens, so these are these quantum fluctuations. They happen in every energy field that we know of. So what we need is we need a giant quantum fluctuation. The bigger the quantum fluctuation, the more rare it is, but what we have here now is we have a basically infinitely sized universe just sitting there for as long as we want. And so anything, no matter how improbable it is, will eventually happen. So you get a big quantum fluctuation in here that suddenly increases the density of dark energy in this tiny, tiny little place, smaller than an atomic nucleus. And what happens is you start expanding that universe into a process that we call inflation, which is something that we think happened in our universe very early on. And that inflation dumps even more energy when it's done into this little piece of the universe that is now basically the same size as our Hubble horizon. And this energy turns into particles. And you create more baryons, you create dark matter, you create everything else, and you basically have a new Big Bang with a new young universe sitting there. So when we say that we see that our universe began 13.7 billion years ago, we don't actually know what happened. We don't know if there was nothing and suddenly there was something, or if we were in an even older universe that was pure dark energy like this one and it suddenly expanded outwards, right? This isn't going to help us, right? This is a long time in the future, but it might very well be that you have this huge old universe that periodically pops out new universes that expand out and become huge old universes that occasionally pop out new universes, right? And so you might actually have an infinitely old thing that periodically portions of it look young. And that's what we're currently sitting in. Pure speculation, no idea if this is correct. But it is one way to try to explain what we see. All right, let me just end. People ask me for reading suggestions, so I'll just leave this up here for questions. This is a book that came out just about a year and a half ago. It sort of covers very recently sort of what people are doing to try to look for this. It's very readable. There's no math. It's what I usually give people now if they want to know more about how we do cosmology. Two slightly older universes that talk specifically about dark matter and dark energy. This one is more about what I talked about, how dark matter and dark energy interact with it. This is really more sort of a discussion of the people involved and how do they go about doing the discoveries and stuff. And finally, if you really want to get into the gruesome math, but don't know general relativity, this book by Barbara Ryden, who's up at Ohio State, is what we actually use to give to our undergraduates to understand how cosmology works. It does require calculus, but it doesn't require any knowledge of general relativity. So, okay.
Questions?
Yeah.
It was, I think it was the near future. It was about 100 billion years.
Yeah.
You mentioned that if the universe is expanding,
No.
if the universe is expanding, then
Right.
eventually we might not be able to see
Right.
the photons coming back. But also earlier in the talk, you talked about getting better and better telescopes, hopefully seeing the beginning of the universe.
Right.
So do we know that that hasn't already happened, to where we'll never be able to see the beginning of the universe?
Not yet. Well, so okay, so Okay, sorry. So the question is basically, as we keep getting better and better telescopes and we keep looking fainter and fainter, are we eventually going to see the galaxies disappearing? I think is.
But has it already happened to where?
Right.
How do we know that it already hasn't expanded fast enough that it's faster than the speed of light?
Okay.
Never seen
So
it
so
yet.
so how do we know that it's expanding? Okay. So basically, it has already happened, and we can see this because what we actually see when we look further and further away is we see further back in time. And with our telescopes that we have right now, we can see all the way out to about redshift 10. So the universe being 11 times smaller than it is now. And that's with our optical telescopes, right? And at that point, we run out of galaxies not because we don't have telescopes good enough to see them. It's because there are no more galaxies. The universe hasn't had time to pull them together and start forming stars. And so we see the biggest galaxies that existed at that time when galaxies started forming and stars started turning on. We can go to a different type of telescope that looks at something called the cosmic microwave background. And with this, we're now looking at something like it's like a redshift 1100. So the universe was 0.1% of its current size. And this was a time when, prior to this, the entire universe looked like a star. The light flying through it was high enough energy that it kept all the hydrogen and helium fully ionized. So the electrons and protons were separated. And that meant that the light was bouncing off the electrons, and you basically had a plasma. And the entire universe was a plasma. As you expand the universe, the redshift, the light gets redder and redder, it gets less energy, and eventually it's not able to keep the hydrogen and helium ionized. So at that point, you combine the universe into atoms, and the light that's there flies free. That light has been redshifting as the universe expands and is currently sitting in what we call the submillimeter. And we can see it with that type of telescope. And what that light will do is, as the universe keeps expanding, it will get longer and longer wavelength. Until eventually people won't be able to see it because the wavelength becomes too big for any telescope that they would think about building. Right? We can see it, and that's actually one of our hints that there is no edge, is we can see it in every direction that we look in. It looks basically the same. In fact, it is disturbingly the same. And it's one of the reasons why we have this idea for inflation occurring in our early universe, is it really should be that because we're looking at this portion of the universe over there back when it was 300,000 years old, and that portion over there, they haven't seen each other yet, and therefore they should have different temperatures, and they don't. And inflation allows us to solve that problem. But that's our biggest view, is that cosmic microwave background. And we get a lot of our cosmology knowledge from those measurements. Yeah. Yeah.
I have two quick questions.
Okay.
The first is, why would the two areas of the universe that have never been in contact with each other be different temperatures?
So why would the two areas? Okay, so what I just explained with the cosmic microwave background, why would they be different temperatures? It's because when you form something, again, you have quantum fluctuations that will say things, or you just have random noise basically. So if we have the early universe being an energy field out of which everything expands, some portions of it are going to be a little bit denser than others, just through natural random processes. And therefore, when that freezes in after everything expands and turns into particles, we would expect some portion to be just a little bit hotter than the other. And if they haven't had time to exchange energy, then they shouldn't equalize out to the same temperature. Is the idea, right? So because we see them as being basically the same temperature, that means that in the past they must have been closer together so they could equalize before they got inflated away. Yeah.
The second question was, if you say we can't observe either dark matter or dark energy,
Yeah.
how do we distinguish them as separate types of energy?
So we can't observe dark matter or dark energy. So how do we distinguish them as being separate? Basically, dark matter is the result of when we look at things that are the size of a galaxy or larger, there is too much gravity. And whatever is causing it, if it seems to be behaving like a particle, so it collapses under gravity and becomes denser, right? And whereas dark energy, whatever is causing it, is this very diffuse thing that exists everywhere and seems to be the same density. Okay. Now, there are ideas to tie dark energy and dark matter into two sides of the same thing. Those get into some of the esoteric ideas where you can explain both of these using a single substance. I'm not going to go into them, but if you want to look, Google dark matter or dark energy, Wikipedia will be happy to list some of them for you. But they get pretty weird. Yeah. Yeah.
The energy of the universe a constant?
Is the energy of the universe a constant? No. So, right? So, and you get this from dark energy. Dark energy has a certain density. It doesn't vary in time. And as we expand the universe, we create more dark energy to keep that density. So as the universe gets bigger, you get more. That's okay. If you took introductory physics classes, we kept saying conservation of energy, conservation of energy. That's actually a lie. Energy is not actually conserved. Energy is conserved under Newtonian mechanics under specific conditions. If you go to general relativity, energy becomes one part of something called the stress-energy tensor, which also includes momentum, curvature of space-time, expansion rate of the universe, and some other things. That stress-energy tensor is overall conserved. And because you derive dark energy from that stress-energy tensor, it is inherently conserved, even though it looks kind of weird. It's basically you're trading off various substances to create the dark energy and keep it conserved.
So it is
So.
constant.
So something is conserved, just not energy. Yeah. Energy, it's kind of like, imagine that you subdivide energy into only light. And you ask, is light conserved? The answer is no, because you can convert other types of energy into light. Yeah. Yeah.
Like you said, dark energy is the least understood part of our universe at this point.
Yes, dark energy is definitely the least understood part. Yes.
Yeah, I'm just wondering what the research status is on this subject.
So what is, okay, so
And then is there any experimental studies, or is experimental studies possible at all?
So basically what are we doing to sort of learn more about dark energy was basically the question. The short answer is the problem that we have right now in trying to do cosmology is we have these really small telescopes that look at very small parts of the sky. And so the Hubble Space Telescope, looks at this area that if you'd look off in the distance and, if you take a sharpened pencil and you hold it out at the end of your arm, the area that the Hubble Space Telescope looks at is about the size of that sharpened pencil tip. It's very small. And therefore, we just haven't covered a lot of the sky very, very deeply. One project that I'm working on right now is a telescope that's being built down in Chile. We're basically going to start in about 4 years. We're going to get a movie of the southern sky every third night. We'll cover the whole sky every third night, so a third of the sky every night. Over 10 years, we add it up, we get the deepest images that we've ever taken over half the sky. What that's going to give us is a lot more data. Anytime which you do this anywhere in science, you basically have your ideas going into it, and then you have what you find in this huge ream of data. And usually what you find is something that you didn't expect, and everything changes. And so that's my expectation, is if I come back in 10 years, 15 years, and talk about this, I will probably have dark energy. We still might not know what it is, but we will at least have ruled out a lot of things because of this vast amount of data. And unfortunately, this is the part that the funding agencies don't want to know. The most likely solution, based on what we currently know, is Einstein's number in a mathematical equation. And if that's true, we'll never know what it is. It will probably be an energy field, but there's so many things that you can do to make that come true that you can't differentiate between them. But we will know what its influence on the universe is, because if it really is that number in that mathematical equation, then everything that I just said comes true.
So with that,
Okay.
everything's going to come true.
Right, exactly.
With that, we'll end the formal part of tonight. I'm sure Doug will be happy to talk to you guys if you want to come up and ask him questions afterwards. A couple things to remember. Next week is Julie Owens on community engaged research, why it matters. The next Science Cafe, Dr. Lawrence Whitmer on digital dinosaurs. And don't forget to sign up for the expo. See you guys later. Thank you very much.
Thank you.